the real action here is, again, not the physical objects that we see, the cells, the tissues, whatever, but what's actually running around are the different patterns. There are patterns in physiological space, there are patterns in cognitive space, there are patterns in anatomical space, and no doubt an infinity of things that we can't even begin to fathom what's going on. And I mean, there's a lot of people in cognitive science that are thinking about it this way, like what are all the the different types of thoughts, the fleeting thoughts, the persistent thoughts, the obsessive thoughts, the personality fragments, the real personality, the transpersonal, the human, whatever it is, right? So, but I think this is also true in the rest of the body. So these, and I think what's really important is that these things, again, this is not some kind of poetry. This is these things should be and are becoming the target of biomedical interventions. So persistent states, not objects, not chemicals, but persistent physiological states that are moving around your body and having different effects. Yeah, it's good science now to find out what are their behaviors, what's the level of cognition there. Can they be communicated with? Can they be trained? Can they have their priors changed so that their behaviors are different? Like this is, and we in our lab on the AI side, we are starting to look at the ecology of thought patterns within artificial agents as well to see, yeah, okay, there's the system that's doing things, but what are the patterns within that system that are doing things?
So hi everyone, my name is Balázs Kegel and this is the iScientist podcast where we explore artificial intelligence, the body and the soul. And this is my great honor today to host Michael Levin. So Michael is a professor of developmental biology at Tufts University and one of my heroes. You are one of the people who not only influence how I do research in AI, because there are a lot of things that I actually changed how I view my work, but you also influenced how I live my life, and this is pretty rare, and we'll see if we can talk about that a little bit. And
talk about it. Yeah.
That's the first time we meet actually. We had a couple of exchanges on Twitter and email, and but I always felt like a close connection to you, and I was thinking why, and it's probably one of them is this sort of like engineering perspective, like it's almost like little kids trying to manipulate the world. Yeah. But at the same time, through my midlife, I also started to think about how to unify the world I'm manipulating and the world I'm living. And so to have a place for me in the world that I'm studying as a scientist or manipulating as an engineer. And I think we have a genuine connection there. But so let's start. I want to talk about deep stuff, because there are a lot of interviews with you on the internet, and of course all the examples will be very welcome. But I want to talk about agencies, especially nested agency and collective agency hierarchies, birth and death, transformation, how those things are related, and maybe a little bit about how, I mentioned that I view the world differently since I'm listening to you, of course, among some others, but it really fits into this changing worldview that I have. So let's start with agency, maybe. Like, how would you explain somebody who hears it in the first time what you mean by agency in biological systems?
Yeah, well, I start by pointing out that we as humans are pretty good at noticing decision making and problem solving in a very narrow part of the spectrum. So medium-sized bodies moving at medium speeds through three-dimensional space. Okay, we're good at that. But it turns out that I think living systems, and to some extent even non-living systems, are navigating many other spaces that are very hard for us to observe. And these are the state of physiological states, the space of anatomical states, of gene expression states, and so on. So what I mean by agency is the ability of a system to meaningfully navigate some kind of space. And that means that it constructs here's the spectrum. If you have a bowling ball on some landscape that has a bunch of wiggles on it, as a third person perspective, your view of the landscape is all you need to know. Okay, from there you know what's going to happen. But if you have a mouse on that landscape, your view of the landscape is far less interesting. What's more important is the mouse's view of the landscape. Otherwise, you cannot make predictions. So that means now you're dealing with a system that has an inner perspective that you have to take into account to be able to do whatever you're going to do. So that's the spectrum of agency. Is to what extent do I need to put myself in the place of the system to look at the world from its perspective, and to say, what do I know, what do I want, what do I believe, and where are my borders, where do I end and the outside world begins, and how much of that do you need to know to meaningfully relate to that system.
Okay, so I really like so if you go down to the cellular level, there's this traditional view that genes are calling the shots, and genes are sort of like blueprints of everything that's happening. And what's surprising about this to me is that, like, if we go up to our level, nobody would say that our muscles are calling the shots, right? So when when I as a person think about myself, you can say a lot of things, but I do feel that I'm calling the shots. So there's sort of like a top-down causation from what I want to my body parts. And when we go into the cellular level, somehow this view of genes calling the shot stuck, whereas what you're saying is more like genes are sort of like a toolbox, and it's really the cell that's calling the shot. So how do you see cognition at the cellular level?
Yeah. Well, there are two pieces to this. One piece is that, I mean, you will find people that say that it's the particles that are calling the shots, right? That at the time of the Big Bang, things got set up, and after that, there is no you, there is no, it's the particles, right? So that's an existing view, and so we can do two things. One is we can ask, to what extent is that view useful? And by the way, now that, I mean, this used to be a philosophical question. Now it's actually an empirical question, because people like Tononi and others, and Sporns and other people have actually developed mathematics that will actually tell you in a given system which level is doing the most work causally, right? So this is no longer just something to sort of hypothetically argue about. You can actually do the work and see. And in some cases, yes, it's the lowest level. In other cases, it's not. And Eric Hole in our center has done amazing work on this, and so on. So, but again, I like models that are useful, not just in explaining past stuff that happened before, but actually both on a personal, and this is where we get to some of the personal stuff, both personally and scientifically, that are generative for new discoveries and new and optimal interactions in the future. So I'll just give you a simple example there. The game of life. Okay, so cellular automaton. So it's a deterministic. You could be a reductionist about it, and you could say, look, there are no gliders. All there is the physics of that world that tell any given pixel if it's going to be on or off in the next generation. That's all there is. And it's not that you're necessarily wrong in the factual sense, and also given a configuration, you can predict everything that's going to happen later. But here's what you can't do. If you don't believe in gliders, you don't believe in this mesoscale, what you're not going to do is create a Turing machine out of our computer out of gliders, right? Because in order to do that, to have that idea and to generate something new, this is not the same thing as predicting forward a starting condition that somebody else set up for you, right? That's fine, but creating a new thing requires you to believe in these mesoscale properties. You will never do that if you don't believe in gliders. And this is why, like, I visualize sometimes, I'm writing something about this, but it isn't done. Trying to play chess with Laplace's demon. Okay, he knows where all the molecules can go, but he doesn't believe in pieces, boards, rules of chess, winning, losing, dominating the center of the board. He didn't believe in any of that stuff. So what he can't do is decide which move shall he make, because they're all equivalent. All the microstates are equivalent to him. There is no mesoscale where some of the outcomes are different than other outcomes, right? So I think so. This view so that's kind of the philosophical part, is that I just think it's not as useful a worldview as understanding that there are higher levels that can take control.
So what concretely, I completely agree with you. So there is this move that in like maybe science less appreciated, less formalized, which is not about having a hypothesis and doing experiments to verify it, but to have another angle from which we look at the phenomenon and then that will trigger some new hypothesis. So if we think about in this way about cells, that they use genes and express the genes as they want to, because they want to do something. So what did it allow you to find if you looked at cells from this point of view?
Yeah, that's very important because I think it's really critical that this is all this business about the agency and unconventional cognition. It can't be just poetry. It's not. I don't say these things because they make me feel good, or because, well, you can look at it this way or you can look at it that way. It's all equivalent. No, then it's no good. You have to be able to show that these things give you some kind of a benefit. So I will describe a few things. The way I give this talk now is around engineering the agential material of life, which is the fact that if you understand that your material is not the same as the passive materials that we've been dealing with for thousands of years, right? Wood, metal, whatever, you can take advantage of some of the amazing higher level control properties, and they give you new capabilities that you couldn't have before. So I'll give you a small example. There are many examples. One thing you can notice is that if you want to, so neuroscientists have this task of neural decoding. Okay, they're going to read the electrophysiology of your brain, and they're going to decode high-level cognitive content. They're going to say, what are your goals? What are your memories? Right, that's the idea, and there's some progress in that. What happens if you apply that technology to the rest of the body? What if you read the mind of the rest of the body? We developed tools about 20 years ago for the first molecular ability to read and write the memory patterns outside the brain. So non-neural tissues. It's called developmental bioelectricity. And what you find is this, that prior to many of the events we care about, so embryonic development, regeneration, cancer suppression, all of these things we're interested in, you can actually look and you can see that the collective, not individual cells, but the collective, has a memory of what it is that it's going to build later. You can read out this memory. In some cases, we can decode it. In many cases, we don't know how to decode it. And then you can read it, but you can also rewrite it. And if you rewrite it, you get exactly what you expect, which is that the collective goes to a different goal. If you rewrite the set point, it will go to a different goal. So when you do this, a few interesting things happen. I'll give you a simple example with eye development. When we look at the face, at the early of a vertebrate face, there is an electrical pattern, which we call the electric face, which tells the cells where the eyes are going to go. It's a very particular electrical pattern that says, put an eye right here. What we did was we introduced that pattern somewhere else in the body, and we found a few interesting things. First of all, it is instructive. So if you introduce it somewhere else, the local cells will say, okay, and they build an eye. We can build an eye on the gut, in the tail, or wherever. That's the first thing. The second thing is the information that we give it is extremely minimal. What we don't do, and this is important for your point about genes, if you thought the genes control the story, what you would be doing is looking to control the individual cell gene expressions to, well, here's some retina, here's some lens, this stem cell has to be optic nerve. You would be in charge of all of that. Instead, what we found out is that you don't need any of that. We discovered a high-level subroutine call, or as I like to, originally I thought of it as a high-level subroutine call. Now I think it's a prompt. It's basically a prompt to the generative model, where what you're doing is you're saying, make an eye here. That's it. We don't say how to build an eye, what size of an eye, what shape of an eye. It's got lots of different substructures, cell types. We don't talk about any of that. We just say build an eye. And so the second thing you find out is it's extremely modular. So you say build an eye, it builds an eye. That's all. You have a simple stimulus that leads to a very complex behavior in anatomical space. That's a key feature of cognitive systems. When you and I are talking, I'm not worried about tweaking your synapses so that you get my point. You do that. I'm passing through a very thin, a thin channel, right? The third thing we find out is that in the developmental biology textbook, they will tell you that only the cells in the front of the head are competent to become I. Well, that's because they were using the wrong prompt. If you use the gene, it's called the master I gene called PAC6. If you use that, then yes, only the cells in the anterior and rectum can make I. But that's because you're using the wrong prompt. If you use the better prompt, for the more convincing prompt for the cells, actually all of them, all the way down to the tail, are competent to do it. And so that's an important lesson in humility for all of us. When you're studying the competency of some in some system, you're really taking an IQ test yourself. Okay, what you're basically finding out is how good am I at talking to the system? How, right? You can't. Anyway, you get the idea. So that's the third thing. The fourth thing we found out is that you don't have to convince all the cells, because because what happens is, if you take a section through that eye, what you'll find is that only a few cells were injected by us. What they did was recruit all their neighbors to participate, and they did it themselves. So we didn't have to teach them to do that. That's the competency of the material. Not only does it build the right thing and then it stops at the right time and whatever, but it also scales the resources to the task. That you didn't have to talk to all of the subunits. Certain subunits take over others. So that's amazing, and it has all kinds of implications for regenerative medicine and so on, that you don't need to affect all the cells. In fact, we've now done it in certain cases like brain repair and cancer normalization. You can do it from the opposite side of the body. It doesn't even have to be anywhere near this information travels long distances through the body. And then the final thing, which I think is kind of the coolest and the weirdest that we're now following up, is what you actually have there. It's not really. I think the better way to think about it, it's not the cells are communicating with they are, but that's not the better way to look at it. What you really have there is a battle of worldviews. What you have is of models. You've injected some information that says you guys should be an I, and the cells that you've injected you've convinced them, they take it on. Now it's time for them to convince the others. But here's the problem. The others, they have a cancer suppression mechanism that says if something nearby has a weird voltage, we need to normalize it out. Okay, and that means electrical synapses, gap junctions, to normalize the voltage. So we actually see this in the embryo. There are early I fields that are formed, and the neighbors, they wipe them out. Not that the cells are still there. It's not the cells that are disappearing. It's that the information is going away. And so sometimes the I message wins, sometimes the stay skin message wins, right? It's the patterns that are actually competing, and to see which one is the most convincing to the medium, which one takes over the medium. And we even have all kinds of weird examples where it really doesn't take much. It's a very like if you take a piece from a two-headed worm, a planarian, and you stick it into a one-headed planarian, in some cases it will take over that message. Not the cells. The cells don't move.
It's more convincing.
The message is somehow more convincing to the larger collective. Very weird, and it takes it over. So the other thing about cognitive systems that I think is very interesting is that they serve as this kind of environment or playground for what I think really is the subject of agency, which are the patterns, the thought patterns. I think all of this is about it's not the physical stuff. This is just I more and more I think that the gene expression and the cell physiology and all of that stuff is that's just the scratch pad. That's just the stigmergic scratch pad of what's really going on, which are the patterns of thought that are kind of battling it out.
Okay, so this leads nicely to the topic I want to talk about, which is, okay, we established pretty much. I mean, you convinced me for sure, but I think even everybody who's listening to you is pretty much sees this way, that you have agency down to wherever we want to look. What is fascinating about this is the nestedness. So you basically have cells. You talk about cell collections or tissues where you can manipulate information using the electrical patterns. And then you go up, you have an organ, and then you have a body, let's say, if we talk about like me. And so it seems that at all of those levels there is agency. And so the things that constitute like a liver, the cells, or the little tissues, I don't know how many levels are there or how many levels are useful to think about, they all have agency, right? So these agencies are nested. And so how does it work? How do they interact? And what is it leads very far. And this is where, my thinking is sort of like, going everywhere. I don't know
Yeah.
how this happens and how this works.
Well, there's a more conventional. I mean, none of this is conventional, but there's a more conventional way, and then a much more crazy thing that I'm going to say. The kind of more conventional thing, I think, is that yeah, we are a massive ecosystem of agents. They're interpenetrating each other, meaning that there are larger agents within which are smaller agents, many levels down. There is communication, cooperation, and competition, both vertically and horizontally. So cells have agendas and they're trying to do what they're trying to do. Tissues and organs are bending the action space for those cells such that whatever they do ends up feeding the larger system, right? And so this goes all the way up. Some of it is very successful, some of it is not, some of it becomes pathological. There are many things that we could talk about in terms of what disease conditions and so on that are involved. But I think that simultaneously, there are many different agents within us, and some of this is known. The thing about the hemispheres, right? That if you put the left hemisphere to sleep with sodium pentothal for 20 minutes, the other one will write down some things that you do not agree with. You do not agree with,
Yes,
right? And
yes.
things like that. So some of this is known, but it's actually way more ubiquitous than that. That's the and I think that's fine. I think that this is not a situation where, like, a lot of people will say that, but this is the problem with panpsychism, is that you have to say how simpler conscious experiences glue together to become this larger. I don't think that's it at all. I don't think it's about that at all of those are there. The subunits are there, and they're having very minimal experiences, and the larger collective has its own that is not the product of these little ones, and we could talk about where it comes from. But there's a weirder piece to this, which is that more and more I think we can say that the real action here is, again, not the physical objects that we see, the cells, the tissues, whatever, but what's actually running around are the different patterns. They're patterns in physiological space, they're patterns in cognitive space, they're patterns in anatomical space, and no doubt an infinity of things that we can't even begin to fathom what's going on. And I mean, there's a lot of people in cognitive science that are thinking about it this way, like, what are all the the different types of thoughts, the fleeting thoughts, the persistent thoughts, the obsessive thoughts, the personality fragments, the real personality, the transpersonal, the human, whatever it is, right? But I think this is also true in the rest of the body. So these, and I think what's really important is that these things, again, this is not some kind of poetry. These things should be and are becoming the target of biomedical interventions. So persistent states, not objects, not chemicals, but persistent physiological states that are moving around your body and having different effects. Yeah, it's good science now to find out what are their behaviors, what's the level of cognition there. Can they be communicated with? Can they be trained? Can they have their priors changed so that their behaviors are different? Like, this is, and we in our lab on the AI side, we are starting to look at the ecology of thought patterns within artificial agents as well, to see, yeah, okay, there's the system that's doing things, but what are the patterns within that system that are doing things?
Okay, so I really liked your cognitive light cone concept, where you say that basically every agent has a size of effect in time and space, and the size of the goals it can think about. And what is a little bit puzzling to me, that the way I imagine is that when lower level agents get together for whatever reason, because they think they can collaborate on something, then how should I imagine it? Is that they themselves will have a larger cognitive cone? Because it somehow felt more natural to me to imagine it like they keep their size of the cognitive light cone, but they together sort of create a new self, a new agent, which has a larger cognitive light cone. And it's sort of and that we can get there, because I have several questions there, but sort of like this high level self emanates into the cells something that is sort of aligned with their capacities and their goals. So they just do what cells do, but somehow, because the collective has now this agency and self, it can coordinate them such that it itself can have a larger effect in time and space. So do you see there's a difference between those, or it's just, it's the same thing?
No, it's very important. So the idea of the cognitive light cone is it's not just the distance that you can sense and affect, it's the size of the biggest goal you can pursue. Okay. And the way I used to tell this story is this: you have let's talk about cells. You have individual cells. When I say goals, I mean things, the cybernetic definition. So meaning it doesn't mean that you have goals. It doesn't have to be metacognitive. It just means that you have some kind of homeostatic or homeodynamic system with a set point that it's trying to reach. Individual cells have very tiny goals. In other words, the only thing they're trying to maintain is that little space around themselves. They have a little bit of predictive power forward, a little bit of memory going backward, and so their cone is quite small. When they become connected electrically, and I'm sure there's other ways to do it. There's probably chemical ways to do it too, but electrically, when they are connected, what happens is they join into a network which does two things. First, it has a computational capacity to remember very grandiose goals. Okay, so instead of managing my pH level in this tiny location, I'm now managing the number of fingers of a salamander limb. And it has a goal, because if you amputate anywhere along the length, they will rapidly rebuild, and then they stop when it's done. Classic homeostasis. So no individual cell knows what a finger is or how many fingers you're supposed to have, but the collective knows. And cells cannot keep this whole information, partly because it's not just the amount of information, it projects into a new space. So individual cells keep their goals in physiological space, metabolic space, but the collective can now keep goals in anatomical space. It now gives you access to a whole new problem space, right? The other thing that happens is something I call memory anonymization. So what happens is when two cells are separate, each one can have independent memories of things that happened and independent goals, and thus they're independent selves. When they merge electrically, it's like a mind meld. It becomes very hard to remember whose memory is whose, because the memory doesn't have metadata about who it belonged to. It's just our memory now, right? And so now you kind of lose your identity a little bit. It becomes very hard to remember your own little goals. You're now this giant thing that's bound together with high causal emergence and all of these kinds of things that have these grandiose goals that you're working on, which bend the action, the action landscape of the smaller pieces. The way that I would say it now, so that's the story I used to tell, and that's the story about cancer, the breakdown of that and the shrinking, right? That's the story that I used to tell. The way I would say it now is a little bit modified, and to get to your point of what happened to the individuals. I think everything that is all physical objects, so simple objects, machines, AIs, cells, embryos, xenobots, all of it, are basically pointers or interfaces to patterns in a Platonic space of patterns. And what I think is happening is that when you're an individual cell, you are a really good resonator for patterns of that scale and that type. In other words, you resonate well with patterns that manage goals about pH and hunger level and things like that. When you join into this larger network, you are not as good a resonator for those, but you become an amazing resonator for much larger scale patterns. And when you become a brainy, mammal, you are now able to have even other, right? So all of these things are there, but you can no longer just the pattern that says go wherever life is good and eat as much as you can and reproduce as much as you can. That pattern is not accessible to you when you're tightly in electrical connection with a whole network. But it can be accessible again if an oncogene comes and disconnects you from your neighbors. You can suddenly start having those thoughts again that you couldn't have when you were mind melded to this thing. So that's kind of the way I think about it now.
I see. Okay, because I thought about more like the cell has its own behavior. It doesn't change if you take it out of the skin. but because it's part of a larger organization now, the constraints that come from above make it behave the way it behaves, right?
I think that's
Or is it the same thing?
I think that's fair. It's just, you could try to tell a mechanical story about this and say that, well, it's this thing is pulling on that thing, and within the tissue there's kind of some stress, and you could try to tell that mechanical story. But of course, you could tell that mechanical story about the computer too, and you can say, bah, it's silicon and copper. It's it's the Maxwell's laws. What else could it be? You're missing the actual causal driver, which is, in the computer case, it's this immaterial algorithm, and in the case of the biology, it's these other things.
No, I'm with you on that. I'm with you that it's just that the will of the higher level agent manifests itself at the cell level as a constraint. You see what I mean? It uses the cell as a tool, and it knows how the cell will behave if I put it into this set of constraints.
I think that's fair. I think that's fair. Constrained, for sure. Anytime we teach anybody anything, we're putting constraints on the space of possible thoughts and actions, right? So fair, but also possibilities, because right, it's not just constraint; it's also possibilities, because you're now providing the ability of these things to do something else. But again, I think I think that by merging into these larger scale subunits, you become less of a transducer of little tiny goals, and you start to implement these other much larger patterns. Right?
I see that. Yeah. So what's the most interesting to me in this, let's say, framework is what the parts think about the whole, and how what do the neurons or my cells think about me, and how does my will or my actions as a higher level agent that consists of these little ones manifest itself at the cellular level? Like, what are the signs for the cell that I'm part of a bigger agent?
That's a great question. I wrote a blog post about this, and I have a picture and a schematic there drawn by Jeremy Gay, that basically there's two neurons in the brain, and they're arguing, right? They're arguing, and the one says, look, we live in a mechanical, cold universe. There's no mind out there. Nobody cares about us. It's just physics and chemistry all the way. And the other one is kind of a mystical neuron, and he says, I don't know. I just have this feeling that in all of this stuff that happens in these waves of back propagation, there's something. I feel like this thing is actually doing something, and it's got there's a larger mind out there, and I mean, in that case, the second one, of course, is correct. And so the question is, right? How do you know? I don't have a great answer for that. I bet there's some kind of Gödel thing that says you can never be sure that you're part of a larger system, I would guess. But I do think that we can acquire evidence for it, even if you can't prove it. And to me, what the evidence would look like is synchronicity. What I think it would look like are events that are connected by meaningful, not by connections at the level of physics. So there's no physical story you can tell from how you got from here to there, but connections that are meaningful mentally, to a cognitive system.
And maybe even this meaning manifests itself higher up, so the meaning is kind of mysterious, no? Because it's a meaning about me, not about the cell's well-being.
Yes, exactly. The meaning will often be only partially accessible, but to the extent that you participate in it at all, it should be relevant to you to some extent, right? So you should capture some of it. If you are part of the system, then the meaning is not going to be completely disjoint and in no way understandable to you. There will be some part of it that you are, sort of tuned into,
yes,
even if you can't see the whole thing.
It's very much like spirituality. That's why I'm laughing, because it's like almost like theology. If we think about our level, right? It's like, because I'm thinking about like the neuron or the skin cell can somehow tap into the space of the agent above, but of course have no idea what's going on, because the goals at the higher level are completely incomprehensible for the cell. But still, there is something there, and that it feels. And maybe, there's the spiritual techniques that we do to try to do this are for. It's sort of like, it's a bigger subject, but we have the scientific method, which basically looks at the system from outside and does hypothesis and tries to predict what will happen. But this move, where we try to tap into another space, another agency, another cognitive system, is a sort of like a first-person move, where we try to become that and imagine what it feels like to be that system. And of course, it calls empathy for agents that are sort of on the same level. Like, I can guess what you feel given what I see, how you behave, and what's around you. But when when you do this vertically, this gets trickier, because of course those systems can have very different goals and very different sensors and actuators and everything. So it's getting harder and harder. But somehow, like, one of the roles of shamans were to get into the skin of a wolf, or get into the skin of the sheep that went away, and find out where it is by actually becoming the sheep, right? And becoming the sheep had all these kind of ritual ways to emulate. So not just understand, but emulate the sheep. And the shaman went out in the forest and got on a sheep skin or a wolf skin and became the wolf, and came back and pointed out where the sheep were, right? So this kind of, like, this connects somehow for me, like the epistemology, but not only from a scientific point of view, but also this sort of like shamanistic method.
Yeah, well, and I think what's I mean, you said from a first person point of view, and I think that's exactly what you have here is from third person science is what's publicly observable effects of these patterns coming into the physical world, and we see what they do for evolution, we see what they do for the physical machines that we make, and so on. But the first person perspective is how that same relationship looks from the other side, right? So the pattern itself, that's what has the first person perspective. And so if you want to join, if you want to see it from the perspective of the higher level system, I think you have to not look at it as the physical separated thing. And now I'm trying the physical embodiment is not going to be able to join up with a larger system. You have to start,
especially that I'm part of it.
Yes, right? Yes, right, right. You have to start from the other side. And if you realize that there is this scale up and this connection on the other end too, then you can say, okay, I can join a different perspective. This is something else I've been trying to draw this idea as, like, basically, like, you can imagine the universe, and then you can imagine like this sphere of different like a soccer ball. I don't know what the geometric name for it is, where you have the different polygons on the surface, and all of these things are different perspectives, right, onto the world, and some are very small and some are much larger, right? And so can you then basically join with systems to look through a bigger interface?
Okay, so the next big topic I want to talk about is time, because of course this is amazing to describe this system as sort of like an existing agency at a certain moment in time, but of course they change. There is a dynamic part of this, and as far as we know, all these things have a birth and a death and some kind of life between the two, and transformation. So even, I'm thinking what you always say, that nothing is black and white. And in a certain sense, even this sort of like on the scale of change, you have very drastic change, like birth and death, we call them, but we just put these labels on them. And there are some transformations or metamorphoses which can be pretty drastic, and some changes that are slower, like aging. And I had a previous guest, Alexander Barth, who's a philosopher. He calls himself a philosopher of time, and he has this grand picture of the universe where the actual book he wrote, his sixth book, is called Process and Event. And he says that basically there are, in the universe, there are these processes that are mostly cyclical. So things come back to the same point and he's approaching it from the point of view of anthropology, like the tribal, seasonal and like life cycle changes that we lived for millions of years. And then there are sometimes big events. And for him, the big event was, of course, when from tribe it started to build empires. And so what he calls event is a drastic change which changes the rules, basically. And so, for example, when life appeared in time, that was something like that, or multicellular life that appeared, he's more interested in the history, like human history, but the nature of these things is the same. And then I was thinking, but if we marry this with this layered ontology, and what's going on is that on the low level, you have events, like a cell is born and the cell dies, and between it lives it out its function. From the point of view of the higher system, it's part of a process. So you have these lower level cycles going on cyclically. On the higher level, the time scale is longer, and in death and birth, there is more time between them, and these little cycles are going on inside if you can go down to molecular level. And that's somehow also true if you start going up from our level into society, like, companies live longer than the people who constitute the companies, or countries, or the whole, humanity. So how do you see this? Because what I'm really interested in is to sort of understand why we die, like the big question. And so I almost feel like there is some natural laws that will be very simple when we discover them, but it's still missing, like how this whole process is governed and how is it related to this sort of layer of ontology that I understand from you.
Yeah. Yeah. I Well, I mean, yeah, the nothing is, I don't feel strongly when I know anything here in this question. It's a very deep question, but we can make some guesses. This idea of, uh, and I think it's an old idea in Buddhism and other traditions, that there are lots of tiny little deaths in us, right? Is that yes, there are bigger ones, but there's also like little tiny ones all along the way. And I think the ultimate version of this is that this bow tie business that I talk about, where you don't have access to the past. What you have at any given moment, the only thing you have access to are the memory traces, the engrams that were left in your brain and body by past versions of you. And you have to reconstruct from that, continuously reconstruct from that, what are you and what should I do, and this going forward. And those are in effect messages from your past self. And so that process of continuous rebuilding and continuous reconstruction, I think, is really critical to what we are, and what guides it. And so what's interesting there is that the compression side of that, it's like a autoencoder kind of thing. The compression side of it, I think, is mechanical, and meaning that it's algorithmic. I think you can compress it algorithmically, and that's fine. But the right side of it, when you take that seed and you have to re-inflate it into something that has saliency for you now, not what it meant for your previous self. And those are memories, I mean, on the genetic scale, on the evolutionary time scale, right? So these are genetic memories. These are morphogenic features. These are cognitive memories. All of those things on different time scales. In order to reinflate them back and into what's salient now, I don't think that's an algorithmic process, because you lost information there. It's like the difference between taking a derivative. You can take a derivative, that's algorithmic, but the integral is creative, because you've lost information, right? You don't know what that is. And so that, I think, uses information from this Platonic space, that's how it's done in some sense. And so in that sense, you can maybe, and so this is all total conjecture, but you can maybe think about that space as, in some important sense, storing state. That is,
Mhm.
I've compressed it in the physical world, and all I have is my engrams, which cannot be fully understood now that I've threw out all the correlations and everything. But with the assistance of what people call, I guess, intuition or cross scale, you can call it synchronicity or whatever. Maybe there's some state saved elsewhere that you can use to be good at reconstructing them, so that you get this persistence of the same hue. I mean, the
Mhm.
you know, the ship of Theseus, yeah, whether you're replacing the planks,
Mhm.
the ship is not the boat. The ship is the plan in the mind of the machinery that keeps up the ship. So the fact that the humans or the robots or whoever it is that are putting new, you know, nailing new boards in, the fact that they have an idea of what the heck a ship is, so they can kind of keep it. There's the ship. The ship is the
Yeah,
pattern. The ship is the
and the
pattern
function.
in the mind of the machinery. So to the extent that these patterns, in the end, I don't think are physical. I think they come from this Platonic space. Maybe it's save state, and maybe that's what enables you to reinflate these constant little deaths that we're having, that every, I don't know, 200 milliseconds or whatever it is, you basically have to reconstruct your whole life story on the fly. But there is a sense of persistence. I mean, sometimes, okay, from child to adult, it gets pretty, you know, banged up, but you know, it butterfly to caterpillar, caterpillar to butterfly, it's much worse, right? The memories do persist, that's known, but they can't, you know, the actual memories of a caterpillar are of no use to the butterfly. You have to remap them onto a different body, different preferences, you know, you have to, but they persist. So I don't know what that says. You know, I'm not going to make any claims right now about what that says about the bigger kinds of deaths that we're talking about, but it is, you know, I'll just say this: I'm not committing to the original. I think this might have been the Platonic idea that the information in that space is static, that it's not changing, right? That it's
Mhm.
eternal and unmovable. I suspect that's not true, and
Uh-huh.
I think that there is change, and if there is change, then that allows it to be to save state in some sense past things that, and again, that state is not physical. These are not physical kinds of scratch pads. These are say me this is connections that have meaning, right?
Yeah, yeah,
Not
no, I understand all of this, and but I think the ship is a good idea to think about because it doesn't seem that we have any natural law that says that we cannot infinitely continue to maintain that ship, right? Yet, anywhere I look in life, it dies. At a certain moment, it dies. So I know you have some ideas about aging and why
yeah.
this happens, and there is the dynamic fascinates me that sometimes you just die a little bit and then you born again on the other side as a caterpillar, or you born again as, like, I know, you go to a spiritual change and it's you look at your past yourself and you don't feel that you are the same person or something like that. I mean, it's you don't have to be schizophrenic, but sometimes it happens such that you still feel the connective connection to this old self, and sometimes it has to go down almost at molecular level and recycle everything, and the thing dies. So this is where I'm thinking about that there must be some kind of natural law that governs this, and it shouldn't be very complicated. If I think about, like, the flatworms, it was almost like one of the extreme example where they almost like managed to uh, turn off they don't distinguish between process and event because they just don't die, and all the cycles they change because they change, but there is no drastic event that we can call death or birth. You
Yeah.
see, so there is like this spectrum, and on this spectrum there must be some law that says what is possible, what is not possible. You see?
Yeah. So right, I was going to bring up the planaria. So I guess I can say two things. I can tell you what my story of the planaria are, and then we can talk about the latest theory of aging that's coming out of our lab. So the story of planaria is this. There's something this drove me crazy for decades, and I think we finally figured out what's going on a couple of years ago. the thing with planaria, okay, highly regenerative, ageless, at least the asexual forms are ageless, cancer resistant, okay? And because the way they reproduce is to tear themselves in half and regenerate, they don't clean the mutations, the somatic mutations, the way that we do for every generation. They inherit them. So you could have they're mixoploid, meaning that every cell could have a different number of chromosomes. So if you take any biology class, what you do not hear is anything that to suggest that the animal with cancer resistance, regenerative powers, and aging and no aging is the one with the dirtiest genome. That's the exact opposite of what you would hear. So what is going on? This is crazy. Why is this happening this way? And I think what's happened, and we've done now computer simulations to show how this works, is that if your material is unreliable, as the planarian substrate is very unreliable, then what happens is much more of the work of evolution goes towards developing a competency software, basically electrophysiological software, whose job it is to make a proper worm no matter what's going on with the hardware. And I don't just mean error correction and redundancy. I mean creative interpretation of what you have to solve your problem under novel circumstances. And this is a positive feedback loop that I think kickstarts intelligence from the beginning of life all the way up. Because what happens is the more intelligence, and initially I'm talking about morphogenetic intelligence, but I think it spills over into conventional kinds of intelligence. The more intelligence you have, the harder it is for selection to see the genome. And what's happening is that if you can't tell the good genome from the bad genome, because both of them ended up fixing all whatever issues they were going to have and give you a nice animal, then basically evolution, this is what our simulations show, is that then evolution ends up doing all of its job on the competency. So I think in planaria it went all the way to the end. They just and then amphibia are all not quite as good, and mammals and like nematodes are just terrible at it. And so so what you have there then is this idea that they do have an important, I mean, they do split, right? And so you could say, but that's their big event, they split. But nevertheless, I think looking at planaria, I don't think we can go with any of the thermodynamic theories of aging, meaning that there's noise accumulating and eventually you have to die. I think, and we already knew that because babies are not born at the age of their parents. Babies are born from zero. So we already knew that you do not just simply keep accumulating stuff. There's obviously a way to clean it up, right? And I think both of those processes are about the intelligence of the material. That's what drives all this stuff. So but our latest theory of aging is basically well, there are two main groups of theories of aging, right? There's the noise and damage theory, that you just accumulate the damage, and then there's the evolutionary theory that says that it's programmed in. There's an evolutionary reason why the old generation has to die, and so it's just it's programmed in. So we have a different type of theory, and our different type of theory, it's basically a psychological theory of aging. Where when I say psychological, I mean all the way down, to the molecules. It's the idea that and we also have a computational simulation paper on this, that a system that is fundamentally a goal pursuing system, like living forms, what does it do when the goal is finished and there is no new goal? And you can start thinking about it that way. Like I always used to think that it was really interesting, the kind of Judeo-Christian version of heaven. You sort of get there and everything's great, but it's great for an infinity amount of time. So can a cognitive system, can a human cognitive system stay sane for an infinity amount of time in the same configuration? I don't know. My gut feeling is that some animals maybe can. Maybe a snake under those circumstances would just kind of be fine forever, every day doing snake things and be fine. Maybe not. I think it would be very interesting, if we could somehow have an answer to that. But humans, I'm sure, you can keep yourself busy for the first 10,000 years, but after that, after a billion years, what are you doing? So what we see, here's what we see in our simulations. If you evolve a system that can pursue a particular goal, and that goal means assemble an embryo. So there's a morphogenetic goal, and so the system works hard to reduce the error and to get to that. But after that's done, it maintains for a while, but then it starts to degrade. And we injected no noise, no damage, there's no reason for it. The reason is a funny thing in these things, but there's no reason for it to start to degrade. But it seems to be an emergent property of goal-seeking systems.
Mm-hmm.
After the goal is met, they kind of start to fall apart if there isn't a new goal. And so
Mm-hmm.
now therapeutically, the question becomes, can we remind them of their original goals so you can just stay a normal human and be young? Or maybe that doesn't work and you have to change it up. And so if you want to live forever, you can be a human for 100 years, but after that you need to make some changes. And I don't know how big those changes need to be, right? It's possible that after that you need to change your embodiment. You can go on, but you need to keep changing it up. We don't, these are all things we don't know yet, but it seems to be that there's a fundamental kind of limitation. So then you have to go back and you say, okay, what's going on with the planaria? Why are they perfectly willing to have the same configuration? And maybe it's this fission, maybe it's the fact that the fission kind of fools you. You divide in half, and you're a simpler organism, and it fools you long enough that you say, oh my God, everything's different now. I'm starting from scratch, and that that does the trick for them. And I don't know what the human version of that is, but
Well, I mean, I just speculate that probably we die because the goal we had becomes irrelevant, maybe because the world is changing around us. So it's a one way of adapting. So it's evolution, but in a higher scale, it's the same thing as cognition. It just maybe you have to look at the population size. But so I think it's just two different strategies, right? The planaria found a way to adapt in a different way, and it smoothed out these big changes. Of course, the fission is a big change, but it still remembers the old self probably in a smoother way than, let's say, I don't know, my molecules remember what I had,
yeah, I mean, you can also, it's kind of funny, but the kind of reproductive, so people will often say, oh, the planaria are amazing because they can regenerate the whole body from a small fragment, right? Well, half the human population can regenerate the whole body from one cell. That's a normal. You could look at normal development as just regeneration. You're down to one cell, and you're going to regenerate. You're going to regenerate the entire body.
Yeah, it's just the planaria self. I just imagine again because I'm not a planaria, but it's itself remembers more its old self than my kid remembers my memories.
Yeah,
that were stored in that cell. You see, so this is what fascinates me. That sometimes there is this huge collapse from the body down to a single cell or even molecules, and sometimes it's more,
yeah,
you know.
yeah. Well,
So
and again,
yeah.
this is totally out there conjecture, but I think we have to keep in mind that when you say we are from the other side, right? From the Platonic space side. So your kid isn't going to remember your memories because your kid is a separate pattern, really, in that space, right? What other memories you might remember when you're born is a whole other question. And there are interesting studies of savants and these kids who at 2 years old somebody gives them a piano and oh yeah, so what you're tuning in there, we could speculate, but anyway, I think it's important to keep in mind that it's actually not the physical stuff that we should be tracking.
Yeah, no, yeah. So the last thing I wanted to add to this is that it reminded me, John Vervaeke has this concept of reciprocal narrowing and reciprocal broadening, which is basically a drug addict is the reciprocal narrowing, the example for the reciprocal narrowing, which is it's reciprocal because what narrows is sort of like the cognitive light cone of the agent. It perceives a smaller and smaller world and smaller goals. So its cognition narrows and the world around it that it perceives narrows. And this is sort of like a pre-death or almost like a walking that phase where the goals like gradually shrink to zero, and if you stay in that state, you will actually die. And then the reciprocal broadening, which he uses for as a concept for spiritual transition or transcendence, is where you go through a phase where you open up your perception, you start perceiving maybe bigger goals or bigger things, and reality changes around you as a consequence of that, the reality that you perceive, and you become, this is like how you can transition from one sort of spiritual state into another, and it's sort of like it has its patterns that you can see everywhere in tradition. And so this reminded a little bit to me to your theory of aging about shrinking goals and disappearing goals and death, and then maybe another way is to like reinvent the goals for which we keep living. See?
Mm-hmm. 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 Yeah.
Okay. Well, I had a lot of other things to talk about, but the time is up.
Well, let's I have to go in a couple minutes, but let's I mean there's plenty more to cover. Let's just schedule another one if you want.
Yeah, super. I'm super happy. Yeah,
Cool.
there's AI. There is also the personal
Yeah,
stuff to
yeah.
talk about. Okay.
I want to talk about I want to talk about the AI and whatever else. So yeah, that's cool. Let's just do another one.
Okay. Well, thank you very much, Michael.
Okay, great to see you. Thanks so
Yeah,
much.
great to
See you
see you.
soon.
Yeah, bye
Bye.
bye.